So in this video we're going to talk about maximums, minimums, and optimization for functions of two variables. This is going to be a little bit of a more lengthy video as there's quite a bit to cover of the basics so that we have time to do some more advanced examples of optimization problems in class. So let's start with some basic definitions that are going to mimic the definitions we made for functions of one variable. So let's start off with a function z is equal to f of xy. We say this function has a local maximum at a point x0, y0 if f of x0, y0 is bigger than every f of xy for all points xy near x0, y0. So what this means, this near x0, y0, is if you think of x0, y0 as a point in the xy plane, then you draw a circle around that point of any size you want. It can be a big circle, can be a small circle, but as long as you can find some circle around that point so that all the points xy that are in that circle, the values of f of xy are less than or equal to f of x0, y0. So you can think of, if you're thinking of your function's graph as kind of like a mountain range, the f of x0, y0 is a local maximum if it's a peak of one of the summits in the mountain range. It doesn't mean it's the tallest mountain overall, but it's the tallest one right there. So analogously, we can define the local minimum at a point x0, y0 if f of x0, y0 is the smallest one. So you can think of this as like a valley, and it's the lowest point in the valley. So all the points around it are the same height or higher up than this point. And then for critical points, we say a point x0, y0 is a critical point of f if the partial derivatives both vanish at that point, so both of them need to be 0, or if either of them is undefined. So you don't need both of them to be undefined, just one of them being undefined is enough to make it a critical point. So let's look at some examples. So this one's fairly straightforward because we have everything basically factored out here. So if we look at the function that consists of x minus 1 squared plus y minus 2 squared, partial derivative is nice and easy to take as from the form of our function. So the partial derivative with respect to x is just 2 times x minus 1, and the partial derivative with respect to y is 2 times y minus 2. It's easy to see both of these partial derivatives are defined everywhere, so our only critical points are going to be where both of them are 0. So the first one, the 2 times x minus 1, this is only going to be 0 when x is equal to 1. And the second one is only going to be 0 when y is equal to 2. So the only point where both of them are 0 is the point 1 comma 2. So that means that this is a critical point for f. And we can see from the graph of f that this is actually a local minimum. So here's our graph. So we're going 2 in the y direction, so 2 in this direction and 1 in the x direction. So that point's like right in here. So we can see that that point is a local minimum for the function. Let's look at another example here. Let's take f of xy to be negative square root of x squared plus y squared. So in this case, when we take the partial derivatives, the partial derivative with respect to x is negative x times, or negative x divided by the square root of x squared plus y squared. And the partial derivative with respect to y is negative y over x square root of x squared plus y squared. So we can see for these partial derivatives, both of them are undefined at the point 0, 0. So that means 0, 0 is going to be a critical number for us. And from the graph, we can see that this is a sharp point and a local maximum. So here at 0, 0, we see we come up to this sharp point. So just how we had in functions of single variables, if you had a sharp point on the graph, the function wasn't differentiable there. It's the same idea here. So we get that these partial derivatives are undefined, and so this is, and we see from the graph it's a local maximum. One more type of example we want to look at before we move on. Let's look at f of xy equals x squared minus y squared. So once again, the partial derivatives are easy to take. So we have f of f sub x is 2x and f sub y is negative 2y. So obviously these are both defined everywhere, so we're only looking at points where they're both 0, and they're both 0 only at the point 0, 0. So that's a critical point, and it's our only critical point for this function. So in this case, this point 0, 0 is called a saddle point, And so if we look at the graph, we can see why. This kind of looks like a saddle. And so 0, 0 would be right about here where the cursor is. And you can see if you were to walk left or right, you go up. So along that path, it looks like it'd be a local minimum. But then if you were to walk out of the screen or into the screen, here we see that then the points go lower. So it's not a local maximum or a local minimum because you can go up or down depending on the direction you walk. So such a point is called a saddle point. So just like with functions of one variable, we have a second derivative test in this case as well to help us determine whether things are local maximums, local minimums, or saddle points. So let's take a critical point, x0, y0, and one where the partial derivatives are both 0, so not one where they're undefined. And so the second derivative test is not going to apply in that case. So let's set d, which is really a function of x0 and y0, but we'll suppress it from the notation just to save some space. So this is the second partial derivative of f with respect to x both times, times the second partial derivative of x with respect to y both times, minus the square of the mixed partial derivatives. So if you have experience with matrices, you can see that this d is the determinant of the matrix where you have f sub xx in the upper left corner, f sub yy in the lower right corner, and then f sub x sub y on off the diagonals. So this is our important quantity for this. So we don't have a single second derivative to look at. So this is kind of taking the place of that. So if we have the situation where d is bigger than 0 and the second derivative with respect to x both times is bigger than 0, then f has a local minimum at that point. So there's nothing special about f sub xx. You could also use f sub yy here. You can't use the mixed partial derivatives, but you can use either of the f sub xx or f sub yy. I just phrased it here with f sub xx because that's how most textbooks do. And you can see, if you're thinking of this in terms of what you already know for functions of a single variable, this f sub xx here being bigger than 0 is kind of giving you the smiley face picture, so that gave us our local minimum. So same kind of situation here with the second partial derivative. If d is bigger than 0 and f sub xx is less than 0, then f has a local maximum at the point. Finally, if d is less than 0, then f has a saddle point at x0, y0. And if d is equal to 0, we gain no information. So we could have a local minimum, a local maximum, or a saddle point, or none of the above at x0, y0. And one can, for the saddle point, we know what local maximums and local minimums look like for functions of one variable. A saddle point you kind of want to think of as the three-dimensional version of the function like y is equal to x cubed. So we know at 0, y equals x cubed, the derivative is 0, but it doesn't have a local maximum or a local minimum there. So if you go one direction, you go down, you go the other direction, you go up. So let's work through an example here where we're going to find the local maximum, the local minimum, and the saddle points for this function. So our first step is to find the partial derivatives. So those are straightforward to find. We find f sub x is x minus 3y minus 9, and f sub y is 9y squared plus 18y minus 3x plus 9. Now the difference from what we've seen in the previous examples here is this isn't easy to see just that for what values of x and y these are both 0, because they're both functions of two variables. So what we're going to do is we're going to set each of them equal to 0 and do some substitutions. So if we set the first one equal to 0, we have x minus 3y minus 9 is equal to 0. We can bring the 3y and the 9 to the other side, so we have x is equal to 3y plus 9. Now what we can do is we can set the second equation equal to 0 as well, and this x here will replace with 3y plus 9, so then we have an equation in just y. And once we do that, then we can go ahead and solve that for y. So once you do that, you can go ahead and factor this. You'll be able to factor a 9 out, and then what's left over you can factor into y plus 2 times y minus 1 is equal to 0. So it might be a good idea at this point to pause the video for a moment and go ahead and do that substitution and do the simplification and the factoring to make sure you get this answer as well. But once we've done this, we see this is going to be 0 when y is equal to minus 2 or when y is equal to 1. And then we can plug those back into the equation for x. So if y is equal to 1, I can plug this back into here, and I'll get 3 times 1 plus 9, which is 12. And similarly, I can plug the negative 2 in here, and I'll get 3 times minus 2, which is minus 6, plus 9, so I get 3. So my two critical points here are 3, negative 2, and 12, 1. And those are all of the critical points, because we can see these partial derivatives are defined everywhere. So now we go ahead and take the second partial derivatives that we're going to need. So if you take the second partial derivative with respect to x, you get 1. If you take the second partial derivative with respect to y, you get 18y plus 18. And then the mixed partial derivative here is negative 3. So if we go ahead and plug these in for d, we'll just do this first for a general x and y since we have 2 points to plug in. We see we get 18y plus 18 times 1, and then minus 3 squared. So this is just 18y plus 9. Now we can plug in our values, and we see that d at the critical point 3, negative 2 is negative 27. So that means that at the point 3, negative 2, this gives us a saddle point of the graph. If we plug in 12, 1, we end up with a positive 27, and we see that f sub xx is always equal to 1, no matter what the point is, and that's positive, so that means 12, 1 gives us a local minimum. So as in the case of functions of a single variable, on certain regions we're guaranteed to have an absolute maximum and an absolute minimum. So for functions of a single variable, it was just if we had a closed interval and a continuous function on the closed interval, the extreme value theorem told us we always had an absolute maximum and an absolute minimum. In this case, we need to worry about what kind of region are we going to look at in the xy plane to get this. So we're going to let R be a subset of the xy plane, so we refer to these subsets as regions, and let's let z be equal to f of xy. So we say that f has an absolute maximum or a global maximum on R at the point x0, y0 if f of x0, y0 is the biggest value for all of the xy's in R. So now you're on a mountain range, and this is the absolute tallest of the mountains on the mountain range. And similarly for absolute minimum, it's the smallest value, so the very lowest point of all of the values. Okay, so same definition as for functions of a single variable, we just have two variables to work with now. Okay, now we want to start talking about what types of regions are we actually going to work with. So we say a region in the xy plane is closed if it contains all of its boundary points. So for instance, if I look at this blue region here, this rectangle, and notice I've filled in the edges of this rectangle with solid black lines here. So that means I'm indicating that this edge of this rectangle is actually part of the set. So in this case, these black lines here are the boundary of the region, and they're all contained in the region. So that's a closed set. On the other hand, if I look at this region, I've used dotted lines here. So that means it's only the blue region, and these points along the boundary, they're not included because it's a dashed line. So you think of the dashed line as kind of the parentheses from functions of a single variable, and the solid line is the square brackets. So this doesn't contain all of its boundary points. In fact, it contains none of its boundary points. So this is not a closed region. We say a region is bounded if one can enclose it in a circle of some large radius r. So for instance, with our region, the last region we looked at there that didn't contain its boundary points, notice I can draw a circle around this. So that means it's a bounded region. If you think of like, for something that wouldn't be bounded, just think of taking the region to be the first quadrant. There's no way to draw a circle around the entire first quadrant. So that would be an unbounded region. So this circle can be arbitrarily large, it just has to be some finite radius r. So then our extreme value theorem in this case says that if we have a continuous function, so again, continuous function just thinks there's no holes in the function, you can draw a nice surface. So if f is a continuous function on a closed bounded region R, then f has an absolute maximum at some point x0, y0 in R, and an absolute minimum at some point x1, y1 in R. So this is the analogous statement to what we had for functions of one variable with the extreme value theorem there. Okay, so let's work through an example now and to see how this is different than what we did in functions of a single variable. So we're going to look at the absolute maximum and absolute minimum of z equals x squared minus y squared. So remember, this was our graph earlier that looked like a saddle. And we're going to look at this on the region given by minus 1 less than or equal to x between minus 1 and 1 and y between minus 1 and 1. And so notice this is exactly the square, or the square region we looked at earlier in blue, where it included its boundaries. So it had the solid black lines along the edge. So here it is pictured again. So we want to find what's the absolute maximum and absolute minimum of this function, but only considering this region here. And here's how the region R would look like when we're thinking in three-dimensional space. So the first thing we're going to do is we're going to find the critical points on the interior of R. So think of this in the function of single variable case when we were doing absolute maximums and absolute minimums. In that case, if we had an interval, we would take the open interval and find the critical point, the critical numbers in the open interval first, and then we would test the boundaries of the interval. So this, we're going to start with the interior. So this is the region we saw earlier with the dashed lines because it's not containing any of the edges. So that's why we have the strict equalities here, or strict inequalities. So we take the partial derivatives, and just like before, we see that it's 2x and minus 2y, and so the only critical point on the interior of R is 0, 0. And when we plug in 0, 0, we get 0. So remember, just like in functions of a single variable, we're going to find critical points, and then we're going to look at the boundary. We're going to take the values and take the biggest one and the smallest one. So on the interior, the only one we'd be concerned with is 0. And we already know this is a saddle point of the function. So now what we have to do is we have to check along the boundary. So when we had functions of a single variable, this was super easy. All we did was plug in the endpoints of the interval, and then you looked at what was the biggest and the smallest from the critical points you found on the interior of the interval and then the edges, and then you were done. However, in this case, we have line segments as our edges of our region, so we can't just plug a line segment in. So we're going to have to actually take the functions and restrict the function f and restrict it to be on those edges, and then we have to do a max-min problem for each one of the edges. So let's start by considering the line segment where x is equal to 1 and y goes between minus 1 and 1. So if we do that, we're only caring about when x is equal to 1, so if we plug that into our function becomes 1 minus y squared. And now I want to look at this function and find its absolute maximum and absolute minimum for when y is between minus 1 and 1. So let's set g of y to be 1 minus y squared, and we're going to find the absolute maximum and absolute minimum on this interval. So we're back to a function of a single variable and an absolute max and absolute min problem for a function of a single variable. So we see g prime of y is equal to minus 2, so that gives me y equals 0 as a critical number. But then this is a function of a single variable over a closed interval, so we have to check the endpoints as well. So our list of possible absolute maximums and absolute minimums of f that come from the line segment where x is equal to 1 are just 1, 0, which came from the interior, and that gives us the value of 1. And then we look at when x is equal to 1, and we look at the endpoints of our interval, so when y is equal to minus 1, and when y is equal to 1. And each of those gives us 0. Now we have to repeat this process for the other 3 edges. So the next one we'll do is when x is equal to minus 1, and we're letting y still vary between minus 1 and 1. So on this line segment, we plug in the minus 1, and we see we still get 1 minus y squared. So we have the same function we're looking at now. G of y is 1 minus y squared. So same process, we see the possible absolute maximums and minimums of f from the line segment when x is equal to negative 1 are f of negative 1, 0, which again gives us 1, f of minus 1, minus 1, which gives us 0, and f of minus 1, 1, which gives us 0. Right, so all these values are coming. We know x is always minus 1, so that's where our x value is coming from. And then the 0 comes from where g prime of y is equal to 0, which is at 0. And then this part, this y equals minus 1, comes from this edge of the interval, and the 1 here comes from this edge of the interval. Now we have 2 more line segments to do where y is equal to 1 and y is equal to minus 1. So we switch now to y being fixed and x going between minus 1 and 1. So on this line segment, we have f of x, 1, is equal to x squared minus 1. So let's go ahead and set h of x to be x squared minus 1. Find the absolute maximum and absolute minimum of this on the interval between minus 1 and 1 for x. So same process as we just did. We take the derivative, we see x is a critical number, and then we also have to check the endpoints. So when y is equal to 1, our possibilities are 0, 1, where f is negative 1, f of minus 1, 1, we're at 0, and f of 1, 1, we're at 0. Now same process for when y is equal to negative 1, just run through everything again. Notice we get the same function. And so when y is equal, just like the case where when y was 1, now with y being minus 1, we get the same values here. 0 minus 1 is equal to minus 1. F of minus 1 is 0, and f of 1 minus 1 is equal to 0. So now we've checked all of the boundaries. So we can go ahead and make our list, just like we would have done for functions of a single variable. And here's our list. So notice I'm saving a little space here by writing this as f of plus minus 1. So this means we saw that f of 1, 0 was 1 and f of minus 1, 0 was 1. So we've done this throughout here to save some space. So we see from this list that 1 is the biggest value and minus 1 is the smallest value. So that means these values are our absolute maximums and these values are our absolute minimums. So absolute maximum is 1 and it occurs at minus 1, 0 and 1, 0. And the absolute minimum is negative 1 and that occurs at 0, negative 1 and 0, 1. So we can go ahead and see this now on when we redo our graph from what we had before. And I put the wrong graph here. So let's go back to, so let me quickly switch this graph out for the correct one. Okay, so here's the correct graph of what it should look like. And so we see our minimums are here when y is equal to, or the value here is negative 1, and these occur when x is equal to 0 and y is either plus or minus 1. And our maximums are up here at 1, and those are occurring when y is equal to 0 and x is equal to plus or minus 1. So we can see on the graph here exactly what we got out of our problem. And notice this is only on this region that we were looking at, this closed bounded region. Obviously, if you extend this, this keeps going down. So there's no absolute minimum or absolute maximum of this function on the entire xy plane. It's only on this interval we looked at where those absolute maximum and absolute minimums exist. Any other closed bounded region would have an absolute maximum and absolute minimum as well. The difficulty is it's not so easy for a general region to evaluate what's going on the boundaries. It worked out nicely for us because they were just line segments, so we could just plug in x is equal to 1 or y is equal to minus 1. And then we do it like an optimization problem for a function of a single variable. But if that region is some weird region or even something that's fairly simple like an ellipse, it still can be much more difficult to do.